The story of the universe begins not with stars, not with galaxies, and not even with space as we understand it today. It begins with a condition so extreme that all familiar concepts of physics collapse into a single, unified state. There is no distance, no time in the way we experience it, and no separation between energy and matter. Everything that will ever exist is compressed into a state of unimaginable density and temperature. This is the beginning of the Big Bang, not an explosion in space, but an expansion of space itself. In the earliest moments, the universe is smaller than anything we can describe using ordinary language. It is not just compact, it is so dense that all fundamental forces are unified into a single framework. Gravity, electromagnetism, and the nuclear forces are not yet distinct. They exist as different expressions of one underlying interaction that we do not fully understand. At this stage, physics as we know it does not yet apply in a complete form. The laws that govern everyday reality have not yet separated into their individual roles. As the universe begins to expand, something extraordinary happens. Space itself stretches outward in all directions. This expansion is not movement through space, but the creation of space itself. Every point in the universe moves away from every other point, not because of an explosion from a central location, but because space is growing uniformly everywhere at once. There is no center to this expansion, no edge, and no boundary. The universe is simply increasing in size as time progresses. In these first fractions of a second, the temperature is so high that no stable particles can exist. Energy dominates everything. Matter and energy constantly transform into one another in a chaotic high-energy environment. The universe is a seething plasma of pure energy, where the usual distinctions between particles do not yet hold meaning. Under these conditions, the rules of quantum physics and gravity are both important, but they are not yet unified into a single consistent theory. As expansion continues, the universe cools slightly. This cooling is crucial because it allows the first distinct particles to begin forming. At extremely high energies, particles can appear and disappear spontaneously. But as temperature drops, these fluctuations begin to stabilize. The first fundamental particles emerge from this energy field. These include quarks and leptons, the basic building blocks of matter. Quarks are especially important because they will eventually combine to form protons and neutrons, which are the cores of atoms. At this stage, however, quarks are still free and unbound. They move through a dense, energetic environment known as a quark-gluon plasma. In this state, the strong nuclear force has not yet confined quarks into larger structures. The universe is still too hot for stable composite particles to exist. As time progresses, the temperature continues to drop due to expansion. This allows quarks to begin binding together. 3 quarks combine to form protons and neutrons, the first stable composite particles in the universe. This process is known as hadronization. It marks an important transition from a universe dominated by free particles to one where structured matter can begin to form. Even though protons and neutrons now exist, the universe is still far too hot for atoms to form. Electrons exist as free particles, constantly interacting with photons and other particles in a dense plasma. Light cannot travel freely through this environment because it is constantly scattered by charged particles. As a result, the universe is opaque. If one could somehow observe it at this stage, it would appear as a bright, foggy glow in all directions. This early phase is sometimes described as the primordial soup of the universe. It is a state of constant interaction where particles collide, scatter, and transform at extremely high rates. Nothing remains stable for long. Yet within this chaos, the foundations of all future structure are being established. As expansion continues, another key event occurs. The ratio of matter to antimatter becomes significant. In theory, matter and antimatter should have been created in equal amounts during the early universe. However, observations show that the universe today is dominated by matter. This implies that a slight asymmetry existed in the early universe, favoring matter over antimatter. The exact reason for this imbalance is still one of the major questions in physics. As particles and antiparticles meet, they annihilate each other, converting their mass into energy. Because there was slightly more matter than antimatter, a small excess of matter remains after most annihilations have occurred. This leftover matter becomes the foundation for everything we see today, including stars, planets, and galaxies. After a few minutes, the universe cools enough for nuclear fusion to begin in a process known as primordial nucleosynthesis. During this period, protons and neutrons combine to form the first atomic nuclei. The most common elements produced are hydrogen and helium, along with trace amounts of lithium. These simple nuclei represent the first chemical structures in the universe. However, atoms themselves cannot yet form because electrons are still too energetic and constantly interacting with photons. The universe remains a hot plasma where light cannot travel freely. This state continues for hundreds of thousands of years. During this time, the universe is still expanding and cooling, but no new large-scale structures have yet formed. Eventually, the temperature drops enough for electrons to combine with nuclei to form neutral atoms. This event is known as recombination. When this happens, photons are no longer constantly scattered by free electrons and can finally travel freely through space. The universe becomes transparent for the first time. The release of these photons creates what we now observe as the cosmic microwave background radiation. This radiation is a snapshot of the universe. At the moment it became transparent, it fills all of space and provides one of the most important pieces of evidence for the Big Bang theory. It shows that the universe was once much hotter and denser than it is today. After recombination, the universe enters a new phase known as the Cosmic Dark Age. Despite the presence of matter and light, no stars or galaxies yet exist. The universe is filled with vast clouds of hydrogen and helium gas, slowly drifting through expanding space. Gravity is the only force shaping these structures, gradually pulling matter together in certain regions. During this period, small fluctuations in density become extremely important. Some regions contain slightly more matter than others. Over time, gravity amplifies these differences. Denser regions attract more matter, becoming even denser, while less dense regions become more empty. This process eventually leads to the formation of the first gravitational structures. The cosmic dark age is a quiet but crucial phase in cosmic evolution. It sets the stage for everything that follows. Without it, the universe would remain a uniform cloud of gas. Instead, it develops complexity through the slow and steady influence of gravity. As density increases in certain regions, gas clouds begin to collapse under their own gravitational pull. As they collapse, pressure and temperature rise at their centers. Eventually, conditions become extreme enough for nuclear fusion to begin. At this moment, the first stars are born. These first stars are very different from stars today. They are much larger, hotter, and shorter lived. Composed almost entirely of hydrogen and helium, they burn their fuel rapidly and shine with intense brightness. Their formation marks the end of the cosmic dark age and the beginning of a universe filled with light. With the ignition of the first stars, the universe undergoes a dramatic transformation. Light now fills space in localized regions, illuminating surrounding gas clouds. Nuclear fusion inside stars begins producing heavier elements such as carbon, oxygen, and iron. These elements will later become essential for the formation of planets and life. The universe is no longer a uniform sea of gas. It is becoming structured, dynamic, and increasingly complex. Stars group together into early galaxies, and gravity continues to shape the large-scale structure of the cosmos. This marks the beginning of a new era in cosmic history, where the simple early universe evolves into a rich and structured cosmos filled with stars, galaxies, and the first seeds of chemical complexity that will eventually lead to planets and life. As the universe continues to expand and cool, the earliest structures of matter begin to take shape in a way that changes everything about its future. In the first chapter, we saw how the universe began in an extreme state of energy and gradually allowed particles, atoms, and finally light to exist freely. Now, in this next stage, we move into a period where the simple ingredients of reality begin to organize themselves into more stable forms. This is the era where the foundation of all future matter is established, and where the universe begins to resemble something that can eventually form stars, galaxies, and planets. In the earliest fraction of a second after the initial expansion, the universe was so hot that energy and matter were interchangeable in a continuous process of creation and destruction. But as expansion progresses, temperature decreases. This cooling is not just a small change. It is the most important driver of structure in the early universe. As energy levels drop, the fundamental forces begin to separate from their unified state. Each force takes on its own identity, shaping matter in different ways. One of the most significant transitions during this period is the separation of the strong nuclear force from the other fundamental interactions. The strong force is responsible for binding quarks together to form protons and neutrons. Once this force becomes distinct, it begins to confine quarks into stable combinations. This marks a major turning point in cosmic history because it allows matter to exist in a more permanent and structured form. Before this confinement, quarks existed freely in a dense plasma, constantly interacting and exchanging energy. This state was extremely chaotic, with no stable particles able to survive for long. But as the universe expands and cools further, quarks become trapped inside composite particles. 3 quarks combine to form a proton or neutron, and this process becomes irreversible under normal conditions in the expanding universe. This transformation is not just a change in particle arrangement, it is a shift in the fundamental nature of matter. Before this moment, the universe was dominated by free energy and unstable interactions. After this moment, stable building blocks of matter begin to exist. These building blocks will eventually form everything from hydrogen atoms to massive galaxies. Once protons and neutrons exist, the universe enters a brief but important phase where nuclear reactions begin to shape its composition. This period is known as primordial nucleosynthesis. It lasts only a few minutes, but its effects last for the entire history of the universe. During this time, the temperature is high enough for nuclear fusion to occur, but not so high that newly formed nuclei are immediately destroyed. In this environment, protons and neutrons collide and stick together to form the first atomic nuclei. The most common result of these reactions is hydrogen nuclei, which consist of single protons. These are the simplest and most abundant building blocks in the universe. Alongside hydrogen, helium nuclei are also formed when protons and neutrons combine in pairs and small groups. Helium becomes the second most abundant element in the universe during this stage. A small amount of lithium is also produced, but heavier elements cannot form because the universe expands and cools too quickly for more complex nuclear reactions to take place. This limitation means that the early universe is chemically simple, composed almost entirely of hydrogen and helium. Despite its simplicity, this composition is extremely important. Hydrogen and helium are the raw materials from which all future stars will be formed. Without this early stage of element formation, there would be no fuel for nuclear fusion in stars, and therefore no light sources to illuminate the universe. After nucleosynthesis ends, the universe continues to expand and cool. However, it remains in a state where electrons are still not bound to nuclei. At this stage, matter exists as a hot, ionized plasma. Photons, or particles of light, are constantly scattered by free electrons, making the universe opaque. Light cannot travel freely, and the universe is filled with a glowing fog of energy. This state continues for hundreds of thousands of years. During this time, the universe is structurally simple but dynamically active. Matter is evenly distributed with small fluctuations in density. These fluctuations are extremely important because they will eventually grow into large-scale structures such as galaxies and galaxy clusters. Gravity plays a central role during this period. Even though the universe is expanding, gravity is constantly working to pull matter together. In regions where density is slightly higher, gravitational attraction becomes stronger, causing more matter to accumulate. In less dense regions, matter becomes more spread out. Over time, this process amplifies small differences into large structures. However, because photons are still tightly coupled to matter, radiation pressure resists the collapse of matter into dense regions. This interaction between gravity pulling matter together and radiation pushing it apart creates a delicate balance. The universe at this stage is stable on large scales, but still evolving internally. Eventually, the universe cools enough for a major transition to occur. Electrons begin to combine with protons and helium nuclei to form neutral atoms. This process is known as recombination, and it marks one of the most important turning points in cosmic history. When electrons bind to nuclei, the number of free charged particles in the universe drops dramatically. As a result, photons are no longer constantly scattered. They are finally able to travel freely through space without obstruction. This moment transforms the universe from opaque to transparent. The light released during this transition is still visible today as the cosmic microwave background radiation. It fills the entire universe and provides a direct snapshot of the cosmos at the moment when atoms first formed. This radiation is incredibly uniform, but it contains tiny variations in temperature that reflect the density fluctuations present at that time. These small variations are extremely important because they serve as the seeds for all future structure. Regions that were slightly denser at the time of recombination eventually grow into galaxies, while less dense regions become vast cosmic voids. The entire large-scale structure of the universe can be traced back to these initial fluctuations. After recombination, the universe enters a period known as the Cosmic Dark Age. Despite the presence of matter and light, there are no stars or galaxies yet. The universe is filled with neutral hydrogen and helium gas, slowly drifting through expanding space. Without sources of light, the universe becomes dark once again, but this time for a different reason than before. During the Cosmic Dark Age, gravity continues its work silently. Over time, regions of slightly higher density begin to collapse. As matter falls inward under gravity, it heats up and forms increasingly dense clouds of gas. These clouds eventually become the birthplaces of the first stars. This process is slow and gradual. It takes millions of years for enough matter to accumulate in a single region to trigger nuclear fusion. But when it finally happens, it marks another major transformation in the universe. The formation of the first stars ends the Cosmic Dark Age. These stars ignite when the pressure and temperature at the center of collapsing gas clouds become high enough for hydrogen nuclei to fuse into helium. This process releases enormous amounts of energy, producing light and heat that illuminate the surrounding universe. The first stars are very different from stars we see today. They are much more massive, often hundreds of times the mass of our Sunday. Because of their size, they burn their fuel extremely quickly and live short but intense lives. Their radiation begins to shape the surrounding environment, ionizing nearby gas and influencing the formation of later structures. With the birth of the first stars, the universe enters a new phase of complexity. Light returns after a long period of darkness, and the first chemical enrichment begins. When these early stars die, they explode in powerful supernovae, scattering heavier elements into space. These elements will later become the building blocks of planets and life. At this point, the universe has fully transitioned from a simple, uniform state into a structured and evolving system. Matter is no longer evenly distributed. Instead, it is organized into regions of increasing complexity, driven by the interplay of gravity, radiation, and nuclear processes. This chapter marks the moment when the universe becomes capable of forming long-lived structures. It is the beginning of a cosmic architecture that will eventually lead to galaxies, solar systems, and the conditions necessary for life. After the first stars ignite and light once again fills the universe, a new era begins. This is not a sudden transformation, but a gradual unfolding of complexity that builds on everything that came before. The universe is no longer a simple, uniform sea of gas. It is now a dynamic environment where gravity, radiation, and nuclear processes interact to shape structure on every scale. In this stage, the foundations of galaxies are laid, and the chemical richness of the cosmos begins to grow. When the first generation of stars forms, they do not appear in isolation. They are born in clusters within dense regions of hydrogen and helium gas. These regions are the result of millions of years of gravitational collapse, where tiny fluctuations in density have grown into significant structures. Gravity is the key force driving this process. It pulls matter inward, compressing it until pressure and temperature become high enough for nuclear fusion to ignite. Once fusion begins, a star becomes a powerful source of energy. Hydrogen atoms in the core are fused into helium, releasing enormous amounts of light and heat. This energy pushes outward, balancing the inward pull of gravity. A delicate equilibrium is established, allowing the star to remain stable for a period of time. This balance is what defines a star's life. However, in the early universe, these first stars are very different from the ones we see today. They are composed almost entirely of hydrogen and helium, with almost no heavier elements. Because of this, they can grow extremely large. Without heavier elements to cool the gas efficiently during formation, these stars often reach masses far greater than modern stars. Their size has a direct impact on their lifespan. The more massive a star is, the faster it burns its fuel. As a result, these first stars live fast and die young on cosmic timescales. Some may only exist for a few million years, which is very short compared to the lifespan of smaller stars like our Sun. During their short lives, these stars have a dramatic effect on their surroundings. Their intense radiation ionizes nearby gas, stripping electrons from atoms and creating regions of ionized plasma. This process carves out bubbles of energetic activity in the surrounding medium. These bubbles grow and expand, shaping the structure of early galaxies. As these massive stars evolve, they begin to produce heavier elements through nuclear fusion in their cores. While hydrogen fusion produces helium, more advanced stages of stellar evolution create elements like carbon, oxygen, and eventually iron. However, in very massive stars, this process happens quickly and leads to instability. When these first stars reach the end of their life cycles, they undergo catastrophic collapse and explode as supernovae. These explosions are among the most energetic events in the universe. In a matter of seconds, a single star can release more energy than an entire galaxy for a short period of time. Supernovae play a crucial role in cosmic evolution. They are responsible for distributing heavy elements into space. Without them, the universe would remain chemically simple, composed almost entirely of hydrogen and helium. But with each supernova, new elements are scattered into surrounding gas clouds, enriching them with the materials needed for more complex structures. These heavier elements are essential for the next generations of stars and for the formation of planets. Carbon, oxygen, silicon, and iron all originate in the cores of massive stars and are spread throughout space when those stars die. Over time, this process transforms the universe from a simple chemical environment into a rich and diverse one. As more stars form and die, regions of space become increasingly enriched with heavy elements. This changes the way gas behaves during gravitational collapse. Heavier elements allow gas clouds to cool more efficiently, leading to the formation of smaller, longer-lived stars. This marks a transition from the first generation of massive stars to more stable stellar populations. At the same time, gravity continues to shape matter on larger scales. Stars begin to cluster together, forming the earliest structures that can be described as proto-galaxies. These are not fully formed galaxies in the modern sense, but rather irregular collections of stars and gas held together by gravity. Within these proto-galaxies, interactions between stars become more common. Gravitational forces cause clusters to merge, separate, and evolve over time. This dynamic environment gradually leads to more organized structures. Over millions of years, these early systems evolve into fully formed galaxies. Galaxies are some of the most important structures in the universe. They are vast collections of stars, gas, dust, and dark matter, all bound together by gravity. In the early universe, galaxies are often irregular in shape, lacking the well-defined structures seen in mature galaxies today. Over time, however, they begin to develop distinct forms, such as spiral and elliptical shapes. The formation of galaxies is deeply connected to the presence of dark matter. Although dark matter does not emit or absorb light, it exerts gravitational influence on visible matter. In the early universe, dark matter forms large-scale structures that act as gravitational scaffolding. Ordinary matter falls into these structures, forming galaxies within them. This relationship between dark matter and visible matter is one of the key factors in shaping the universe. Without dark matter, galaxies would not form in the way we observe. It provides the gravitational framework necessary for ordinary matter to accumulate and organize into complex structures. As galaxies form and evolve, they often interact with each other. Collisions and mergers between galaxies are common events in cosmic history. When galaxies collide, their individual stars rarely collide directly due to the vast distances between them. Instead, the galaxies pass through each other while their gravitational fields interact, reshaping their structures. These interactions can trigger bursts of star formation as gas clouds are compressed during the collision. Over time, repeated mergers can transform galaxy shapes, turning spiral galaxies into elliptical ones or creating entirely new structures. The universe is therefore constantly evolving, with galaxies growing and changing through interaction. At the centers of most galaxies, including those formed early in cosmic history, something extraordinary begins to develop. Massive concentrations of matter collapse under gravity to form supermassive black holes. These objects are millions or even billions of times more massive than the Sun and play a crucial role in galaxy evolution. Supermassive black holes influence their surroundings through intense gravitational fields. As matter falls into them, it forms accretion disks that emit enormous amounts of radiation. These active galactic nuclei can outshine entire galaxies for periods of time, affecting star formation and the distribution of gas. The presence of supermassive black holes suggests that galaxy formation and black hole growth are deeply connected processes. As galaxies evolve, their central black holes grow as well, creating a relationship between the largest structures in the universe and the most extreme gravitational objects. During this era, the universe becomes increasingly structured and complex. Galaxies form large-scale networks known as the cosmic web. This web consists of filaments of galaxies separated by vast voids. Matter is not evenly distributed but organized into a large interconnected pattern shaped by gravity and dark matter. This structure reflects the influence of initial density fluctuations from the early universe. Tiny variations in density have grown over billions of years into massive structures spanning hundreds of millions of light years. The universe is no longer uniform. It is a highly structured system with layers of organization. Within galaxies, star formation continues. New generations of stars are born from gas enriched by previous generations. These stars have higher metallicity, meaning they contain more heavy elements. This allows for more complex planetary systems to form around them. As time progresses, planetary systems begin to appear around many stars. These systems form from rotating disks of gas and dust left over from star formation. Within these disks, particles collide and stick together, gradually forming larger bodies such as planets, moons, and asteroids. This process leads to the emergence of diverse planetary systems throughout the universe. Some of these planets may have conditions suitable for liquid water and complex chemistry. In at least one known case, these conditions eventually lead to the emergence of life. By this stage in cosmic history, the universe has transformed from a simple, expanding plasma into a rich and structured environment, filled with galaxies, stars, and planets. The seeds planted in the earliest moments of the Big Bang have now grown into a vast and evolving cosmos. This chapter marks the transition from a universe dominated by simple physical processes to one shaped by complex interactions between gravity, nuclear physics, and chemistry. It is the beginning of cosmic structure on a grand scale, setting the stage for the formation of worlds and eventually the emergence of observers who can look back and begin to understand the universe itself. After the universe becomes filled with galaxies, stars, and the first planetary systems, it enters a long and complex phase of evolution where structure continues to grow, collide, and transform. This is not a quiet or static era. It is a time of constant motion on a cosmic scale, where gravity continues to shape everything and the universe becomes more chemically diverse, more structurally complex, and more dynamic than ever before. In this stage, the universe begins to resemble the cosmic web, we observe today, a vast, interconnected system of galaxies separated by enormous empty regions of space. The distribution of matter in the universe is not random. It is shaped by the invisible influence of dark matter, which forms the backbone of cosmic structure. Dark matter does not emit light, but it interacts through gravity. In the early universe, slight fluctuations in density were amplified over billions of years by gravitational attraction. Regions with slightly more matter attracted even more matter, while less dense regions became emptier. This process created a network of filaments, clusters, and voids. These filaments are enormous structures made up of galaxies and gas stretching across hundreds of millions of light years. At the intersections of these filaments, where matter is most concentrated, large galaxy clusters form. These clusters are some of the most massive structures in the universe, containing thousands of galaxies bound together by gravity. Between these dense regions lie vast cosmic voids, where very few galaxies exist and matter is extremely sparse. This large-scale structure is often called the cosmic web because of its interconnected web-like appearance when mapped in 3 dimensions. It is one of the most important features of the universe at large scales, and it reflects the underlying distribution of both visible matter and dark matter. As galaxies move through this web, they are not static. They interact, collide, and merge over time. Galaxy collisions are not rare events. In fact, they are a natural part of cosmic evolution. When 2 galaxies approach each other, their mutual gravitational attraction pulls them together. Over time, they pass through each other and their shapes are dramatically altered. During these interactions, stars within galaxies rarely collide directly because of the vast distances between them. Instead, the gravitational fields of the galaxies interact, distorting their shapes and redistributing their contents. Gas clouds within the galaxies can be compressed during these encounters, triggering bursts of star formation. These events can temporarily increase the brightness of galaxies as new stars are rapidly formed. Over long periods, repeated collisions can completely transform galaxies. Spiral galaxies can be disrupted and turned into elliptical galaxies. Smaller galaxies can be absorbed into larger ones. This process of hierarchical growth means that larger galaxies are often built from the merger of smaller systems over billions of years. At the same time, the internal evolution of galaxies continues. Within galaxies, stars live out their life cycles, forming, evolving, and eventually dying. Each generation of stars contributes to the chemical evolution of the universe. When stars die, especially in supernova explosions, they release heavy elements into space. These elements enrich the surrounding gas, changing its composition over time. This chemical enrichment is extremely important for the formation of planets and life. Early in the universe, only hydrogen and helium existed in significant amounts. But as generations of stars lived and died, heavier elements such as carbon, oxygen, nitrogen, silicon, and iron became more abundant. These elements are essential for the formation of rocky planets and complex chemistry. With each cycle of star formation and destruction, the universe becomes more chemically diverse. New stars form from enriched gas clouds, and these stars are more likely to have planetary systems. Around these stars, dust and gas in rotating disks begin to clump together, forming planets over time. Planet formation is a slow and complex process. Within a protoplanetary disk, particles collide and stick together, gradually building larger and larger bodies. These bodies eventually become planets, moons, and other smaller objects such as asteroids and comets. The composition of these planets depends on their distance from their host star and the materials available in the surrounding disk. In inner regions of planetary systems, where temperatures are high, rocky planets form from heavier elements. In outer regions, where temperatures are lower, gas giants can form by accumulating large amounts of hydrogen and helium. This diversity of planetary systems is a direct result of the chemical evolution of the universe. As galaxies continue to evolve, some of them develop extremely energetic centers. At the cores of many galaxies lie supermassive black holes. These black holes are millions or even billions of times more massive than the Sun and have a profound influence on their surroundings. When large amounts of matter fall into these black holes, they form accretion disks that release enormous amounts of energy. These active galactic nuclei can outshine the entire galaxy in which they reside. They emit intense radiation across the electromagnetic spectrum, including visible light, X-rays, and radio waves. This energy can affect star formation in the surrounding galaxy by heating gas and preventing it from collapsing into new stars. The relationship between supermassive black holes and their host galaxies is one of the most important areas of modern astrophysics. Observations show that the mass of a galaxy's central black hole is closely related to the properties of the galaxy itself. This suggests that the growth of black holes and galaxies is interconnected, possibly through feedback processes that regulate both. As time continues, the expansion of the universe itself plays an increasingly important role. The universe is not only expanding, but this expansion is accelerating due to a mysterious force known as dark energy. Dark energy acts as a property of space itself, causing the rate of expansion to increase over time. This accelerated expansion has important consequences for cosmic structure. Distant galaxies are moving away from each other faster and faster. Over extremely long timescales, this will lead to a situation where galaxies outside our local group will become unreachable, as their light will no longer be able to reach us. In the present era, however, the universe is still rich with interaction. Galaxies are still forming, merging, and evolving. Star formation continues in many regions, especially in spiral galaxies, where gas is still abundant. The universe is active and dynamic, filled with ongoing processes of creation and destruction. Within this evolving universe, there are also regions of extreme physics. Neutron stars, black holes, and other compact objects represent the final stages of stellar evolution. These objects are remnants of massive stars that have exhausted their nuclear fuel and undergone collapse. They are incredibly dense and exert strong gravitational influence on their surroundings. Neutron stars are formed when the core of a massive star collapses under gravity, causing protons and electrons to combine into neutrons. The result is an object with the mass of a star, compressed into a sphere only a few kilometers in diameter. Black holes represent an even more extreme outcome, where gravity becomes so strong that not even light can escape. These compact objects play an important role in shaping their environments. They can emit jets of high-energy particles, influence nearby matter, and in some cases merge with each other, producing gravitational waves. These waves are ripples in space-time itself, carrying information about some of the most energetic events in the universe. The detection of gravitational waves has opened a new window into the universe. It allows scientists to observe events that were previously invisible, such as black hole mergers and neutron star collisions. These observations confirm predictions made by general relativity and provide new insights into the behavior of extreme gravity. As we move through this stage of cosmic evolution, the universe becomes a place of both creation and destruction. Stars are born from collapsing gas clouds, and stars die in violent explosions. Galaxies grow through mergers, and structures are shaped by both visible and invisible matter. This ongoing cycle of change is what defines the middle era of the universe. It is a period of maximum complexity, where all the major components of cosmic structure are active and interacting. It is the stage in which the universe reaches its peak level of diversity in structure, chemistry, and physical processes. In the next stage of cosmic evolution, we will see how this complexity begins to slow down as star formation declines, galaxies age, and the universe gradually transitions toward a more quiet and distant future. As the universe continues its long evolution, it begins to enter a phase where the most active period of creation slowly starts to change. Galaxies are still forming stars, black holes are still feeding on surrounding matter, and cosmic structures are still interacting, but the overall intensity of these processes begins to shift. This is not an abrupt transition. It is a gradual change that unfolds over billions of years. As the available raw material for star formation begins to decrease, and the universe slowly moves toward a more stable and quieter state. At the heart of this transformation is the simple fact that stars consume the very material that gives birth to them. Every star forms from clouds of gas, primarily hydrogen and helium, that collapse under gravity. Inside these stars, nuclear fusion converts hydrogen into heavier elements, releasing energy that powers the star's light. Over time, this process depletes the available hydrogen gas in galaxies. As more and more stars are formed and die, the reservoir of star-forming material gradually diminishes. In the early and middle stages of the universe, gas clouds were abundant and widely distributed throughout galaxies. Star formation occurred at high rates, especially in regions where gas density was high. But as time passes, much of this gas becomes locked into stars, planets, or expelled into intergalactic space by energetic events such as supernovae and black hole activity. This leads to a natural decline in the rate of new star formation. This decline does not happen uniformly across the universe. Some galaxies continue to form stars at high rates, especially those that still contain large amounts of cold gas. These are often spiral galaxies with active star-forming regions. In contrast, many elliptical galaxies have already used up most of their gas and now contain older, redder stellar populations. These galaxies are often referred to as red and dead, because they no longer produce significant numbers of new stars. As star formation slows, the overall appearance of the universe begins to change. In earlier epochs, the universe was filled with bright, blue, massive stars that burned hot and lived short lives. These stars dominated the light output of galaxies and made the universe appear more active and dynamic. In the current era, however, longer-lived, smaller stars become more dominant. These stars burn their fuel slowly and emit less intense light, giving galaxies a more subdued appearance. The life cycle of stars plays a central role in this transformation. Massive stars, which dominate early star-forming regions, have short lifespans measured in millions of years. They end their lives in supernova explosions, enriching the surrounding medium with heavy elements and triggering new waves of star formation. But as gas becomes less available, fewer massive stars are formed. Instead, smaller and more stable stars become the norm. These smaller stars, such as red dwarfs, can live for billions to trillions of years. They burn their fuel slowly and steadily, making them extremely long-lived compared to their massive counterparts. As the universe ages, these low-mass stars begin to dominate the stellar population. This shift marks a transition from a universe dominated by short-lived energetic processes to one dominated by long-lived, stable systems. At the same time, galaxies themselves continue to evolve through gravitational interactions. While large-scale galaxy formation through mergers becomes less frequent as the universe expands and structures become more isolated, interactions still occur, especially within galaxy groups and clusters. These interactions can slowly reshape galaxies, stripping gas, altering orbits, and redistributing matter. In some cases, galaxies within clusters can experience a process known as ram pressure stripping. As a galaxy moves through the hot, diffuse gas of a galaxy cluster, its own gas can be stripped away by pressure. This further reduces its ability to form new stars. Over time, this process contributes to the overall decline in star formation across the universe. Meanwhile, supermassive black holes at the centers of galaxies continue to influence their environments. Even as star formation decreases, these black holes remain active in some cases, especially when they are fed by remaining gas or by material from disrupted stars. When active, they can release enormous amounts of energy, affecting the surrounding galaxy and regulating further star formation. This feedback process is an important part of galaxy evolution. Energy released by black holes can heat surrounding gas, preventing it from cooling and collapsing into new stars. In this way, black holes act as regulators of galaxy growth, helping to determine how and when star formation occurs. As the universe continues to expand, distances between galaxies increase. Dark energy drives this expansion, causing the rate at which galaxies move away from each other to accelerate over time. As a result, more and more galaxies pass beyond the observable horizon, meaning their light will never reach distant observers in the far future. In the current era, we can still observe a vast number of galaxies, but this will not always be the case. Over extremely long timescales, only galaxies that are gravitationally bound to each other will remain accessible. For example, the galaxies in the local group, including the Milky Way and Andromeda, will eventually merge and form a single large galaxy. This future merged galaxy will contain all the stars and stellar remnants of its predecessors. Over time, it will become an isolated island of matter in an ever-expanding universe. Outside this local structure, the rest of the universe will become increasingly distant and difficult to observe. As star formation declines and galaxies age, the universe enters what is sometimes called the degenerate era. In this phase, most of the luminous energy output comes from long-lived stars and compact objects, such as white dwarfs, neutron stars, and black holes. These objects represent the final stages of stellar evolution. White dwarfs are the remnants of stars like our Sun. After such stars exhaust their nuclear fuel, they shed their outer layers and leave behind a dense core composed mainly of carbon and oxygen. This core slowly cools over time, emitting residual heat but no longer undergoing fusion. Neutron stars are even more extreme remnants, formed from the collapse of more massive stars consisting primarily of densely packed neutrons. Black holes represent the final stage for the most massive stars. They contain regions of space-time where gravity is so strong that nothing, not even light, can escape. In the long term, black holes may become the most dominant objects in the universe, as all other forms of stellar activity gradually fade. During this era, the universe becomes darker and more isolated. Star formation has largely ceased, and existing stars slowly burn out over time. The cosmic landscape shifts from one filled with bright, active galaxies to one dominated by faint, long-lived remnants and dark, massive objects. Despite this decline in visible activity, the universe is still far from static. Gravitational interactions continue to shape the motion of objects. Black holes may continue to grow by absorbing matter or merging with other black holes. Over extremely long timescales, even these objects are expected to slowly evaporate through quantum processes such as Hawking radiation. As black holes lose mass through this process, they gradually shrink and emit radiation. In their final stages, they may release bursts of high-energy particles before disappearing completely. This marks a potential endpoint for one of the most important classes of objects in the universe. At this stage of cosmic evolution, the universe has undergone a profound transformation from a hot, dense state filled with energy and rapidly forming structures to a cold, expanding system dominated by long-lived remnants and slow processes. The most active era of star formation is now behind, and the universe is transitioning toward a quieter future. However, even in this quieter phase, the universe remains rich with physical processes. Gravity still operates, black holes still exist, and particles continue to interact. The universe is not dead, but it is evolving toward a state of lower energy and reduced activity. This chapter marks the beginning of the universe's long decline in energetic complexity. It is the transition from a vibrant, star-filled cosmos to one that is gradually cooling, expanding, and becoming more isolated. In the next stage, we will explore how this process continues into the far future, where even the last stars begin to fade and the universe moves toward its ultimate fate. As the universe continues its long and inevitable expansion, it enters a stage where the most dramatic and energetic processes of cosmic history begin to fade. The brilliance of young galaxies, the rapid birth of massive stars, and the frequent collisions that once shaped the large-scale structure of the cosmos slowly give way to a quieter, more isolated universe. This is not a sudden change, but a gradual transition over billions and even trillions of years, where the universe moves from activity towards stillness, from creation towards slow transformation, and from complexity toward simplicity. At this stage, the most important driver of change is no longer star formation. Instead, it is the depletion of usable material. Hydrogen gas, the primary fuel for stars, becomes increasingly scarce within galaxies. Much of it has already been converted into stars or expelled into intergalactic space by energetic processes such as supernova explosions and black hole activity. Without fresh gas inflows, galaxies slowly exhaust their ability to form new stars. In earlier eras, galaxies were vibrant regions of constant creation. Spiral arms were filled with glowing nebulae, where dense clouds of gas collapsed to form new stellar systems. Massive stars burned brightly, lived briefly, and ended in spectacular supernova explosions that enriched the universe with heavy elements. These processes were common and continuous, shaping galaxies into dynamic and evolving systems. But as time passes, this cycle begins to weaken. Star formation rates decline across most galaxies. The spiral arms that once shimmered with bright blue stars become less active. Instead, they are populated by older, cooler, and redder stars that shine more steadily but less intensely. The overall appearance of galaxies changes, shifting from bright and active to dimmer and more stable. This transition is particularly evident in elliptical galaxies. These galaxies often contain older stellar populations and very little gas or dust. As a result, they no longer produce significant numbers of new stars. Their light is dominated by long-lived stars that formed billions of years earlier. Over time, these galaxies become increasingly quiet, serving as relics of earlier cosmic activity. Even in spiral galaxies, where some star formation continues, the rate of new star creation gradually decreases. Without sufficient gas density, the gravitational collapse needed to form new stars becomes less frequent. The interstellar medium, once rich with dense molecular clouds, becomes more diffuse and less capable of supporting widespread star formation. One of the key reasons for this decline is the role of feedback processes. In earlier epochs, energetic events such as supernovae and active galactic nuclei helped regulate star formation by injecting energy into surrounding gas. While these processes can sometimes trigger star formation by compressing gas clouds, they can also heat and disperse gas, preventing it from collapsing. Over long periods, this feedback contributes to the gradual depletion of star-forming material. Another important factor is the expansion of the universe itself. As space continues to expand, galaxies become more isolated from one another. Gas that might have been exchanged between galaxies in earlier times becomes less likely to interact. This isolation reduces the overall availability of fresh material for star formation within individual galaxies. Meanwhile, the stars that already exist continue their natural life cycles. Massive stars, which played a major role in shaping early galaxies, are now increasingly rare. Their short lifespans mean that they have already lived and died in earlier cosmic epochs. What remains are primarily long-lived, low-mass stars that burn their fuel slowly over billions or even trillions of years. These low-mass stars, such as red dwarfs, become the dominant stellar population in the universe. Unlike massive stars, which shine brightly but briefly, red dwarfs are dim but extremely stable. They consume their fuel at a very slow rate, allowing them to remain active for timescales far exceeding the current age of the universe. In the far future, these stars will represent the last remaining sources of sustained nuclear fusion. As the universe continues to age, even these long-lived stars will eventually exhaust their hydrogen fuel. When this happens, they will no longer be able to sustain nuclear fusion in their cores. For stars like the Sun, this leads to a transformation into a white dwarf. The outer layers are expelled, forming planetary nebulae, while the core remains as a dense, cooling remnant. White dwarfs are incredibly dense objects. A mass comparable to the Sun is compressed into a volume roughly the size of Earth. Although they no longer produce energy through fusion, they continue to emit residual heat, slowly cooling over time. In the far future, they will fade into dark, cold remnants. More massive stars that already ended their lives earlier have left behind neutron stars or black holes. Neutron stars are composed almost entirely of neutrons packed into an extremely dense state. They are among the most compact forms of matter in the universe. Black holes, on the other hand, represent regions where gravity has collapsed matter beyond known physical limits, forming horizons from which nothing can escape. As time progresses, these compact objects become increasingly important. With fewer active stars, the universe becomes dominated by remnants of past stellar evolution. White dwarfs, neutron stars, and black holes form a new kind of cosmic landscape, one that is quiet, dark, and slowly evolving. In some cases, these objects can still interact. Binary systems involving white dwarfs or neutron stars can emit gravitational waves as they orbit and eventually merge. Black holes can also merge, producing powerful bursts of gravitational energy. These events are among the last remaining dynamic processes in an aging universe. However, even these interactions become increasingly rare as time continues. The universe expands further and objects drift farther apart. Gravitational interactions weaken over vast distances, and the frequency of collisions and mergers decreases. The universe becomes more isolated, with structures slowly drifting apart from one another. At the same time, supermassive black holes at the centers of galaxies continue to exist as long-lived anchors of gravitational structure. In the absence of new material to consume, their activity gradually diminishes. They become quieter over time, no longer powering luminous active galactic nuclei. Instead, they enter a dormant state, slowly evolving through extremely long timescales. The large-scale structure of the universe also continues to evolve. The cosmic web that once connected galaxies through vast filaments of matter becomes less dynamic. As galaxies move apart due to cosmic expansion, these connections weaken. The universe becomes more fragmented, with isolated clusters of matter surrounded by increasingly empty space. In the far future, each gravitationally bound system will evolve independently. The local group of galaxies, for example, will eventually merge into a single large galaxy. Beyond that, no new external interactions will occur due to the accelerating expansion of space. Each such system becomes a self-contained island in an expanding void. Within these isolated systems, stellar evolution continues on very long timescales. Red dwarfs remain the last active stars slowly burning their hydrogen fuel. Eventually, even they will exhaust their energy sources and fade. At that point, no new stars will form, and the universe will enter a state dominated entirely by stellar remnants. As this process unfolds, the universe becomes increasingly dark. The number of light sources decreases dramatically. The night sky, which today is filled with billions of galaxies, will, in the distant future, contain only isolated points of light, and eventually none at all. Despite this fading brightness, the universe is still governed by the same fundamental laws of physics. Gravity continues to operate, quantum processes still occur, and particles still interact. However, the overall level of energy in the universe steadily decreases, leading to a gradual approach toward thermodynamic equilibrium. This stage of cosmic evolution is sometimes referred to as the degenerate era, or the era of stellar remnants. It represents a transition from a universe driven by nuclear fusion and star formation to one dominated by long-lived remnants and slow gravitational interactions. In this era, the universe is still structured, but its activity is greatly reduced. The processes that once shaped galaxies and produced new stars are now largely complete. What remains is a vast and aging cosmic environment slowly evolving toward equilibrium. This chapter represents the beginning of the universe's long decline in energy and activity. It is a universe that still exists, still evolves, but does so at an increasingly slow and subtle pace. In the next stage, we will move even further into the future, where even the last stars disappear. Black holes dominate the cosmic landscape, and the universe approaches its final possible states. As the universe continues its passage through deep time, it enters a stage where the familiar structures of galaxies, stars, and planetary systems have largely completed their evolutionary cycles. The cosmos is no longer dominated by bright active star formation or frequent galactic collisions. Instead, it is shaped by remnants of earlier eras, slow gravitational interactions, and the long-term behavior of the most extreme objects in nature. This is the beginning of a universe where energy becomes increasingly rare and where structure persists more than creation. At this point in cosmic history, most of the stars that once filled galaxies have already gone through their full life cycles. Massive stars lived fast and died early, leaving behind neutron stars and black holes. Medium-sized stars, like our Sun, have transformed into white dwarfs after exhausting their nuclear fuel. Only the smallest and longest-lived stars, red dwarfs, continue to shine, but even they are slowly burning through their limited hydrogen reserves. Because star formation has largely declined, the universe is no longer producing new generations of stars at significant rates. The gas clouds that once filled galaxies and enabled starbirth have been consumed, dispersed, or heated beyond the point where gravitational collapse can easily occur. Without fresh material, the cycle of stellar creation slows to a near halt. Galaxies themselves are still present, but their appearance has changed dramatically. In earlier eras, spiral galaxies displayed bright arms filled with young blue stars, glowing nebulae, and active star-forming regions. Now, these features are fading. The spiral arms become less distinct as the young stellar population disappears. What remains are older stars, distributed in more stable and less active configurations. Many galaxies evolve into elliptical forms over time due to repeated mergers and the gradual loss of gas. These elliptical galaxies contain large populations of old stars and very little interstellar medium. As a result, they no longer produce significant new stars. They become stable, long-lived structures, slowly aging without major internal transformation. In this era, gravitational interactions between galaxies become less frequent. The expansion of the universe, driven by dark energy, increases the distance between galaxy groups. Only gravitationally bound systems remain connected. Galaxies that are not gravitationally bound to each other continue to drift apart, eventually becoming unreachable from one another due to the accelerating expansion of space. Within gravitationally bound systems, however, evolution continues on smaller scales. Galaxy groups and clusters still contain multiple galaxies interacting through gravity. Over extremely long timescales, these galaxies can merge into larger structures. In some cases, entire galaxy clusters may collapse into single massive elliptical galaxies. These mergers are slow but inevitable outcomes of gravitational attraction. As galaxies merge, their central supermassive black holes also move toward each other. Over time, these black holes can form binary systems and eventually merge themselves, releasing enormous amounts of energy in the form of gravitational waves. These waves ripple through space-time, carrying information about some of the most massive and energetic events in the universe. However, as time continues, even these dramatic events become less common. The universe expands further, and the density of matter decreases on large scales. Fewer interactions occur between galaxies, and the frequency of mergers declines. The universe becomes increasingly quiet on cosmic scales. Within individual galaxies, the dominant objects become stellar remnants. White dwarfs, neutron stars, and black holes represent the final stages of stellar evolution. These objects no longer produce energy through nuclear fusion, but they remain active in other ways. White dwarfs slowly cool over time, neutron stars rotate and emit radiation, and black holes interact gravitationally with their surroundings. White dwarfs are particularly important in this era. They are the remnants of stars that were not massive enough to become neutron stars or black holes. After shedding their outer layers, they remain as dense cores composed primarily of carbon and oxygen. Although they no longer produce fusion energy, They continue to radiate heat for extremely long periods, slowly cooling as the universe ages. Neutron stars represent an even more extreme state of matter. Formed from the collapse of massive stars, they are composed almost entirely of neutrons, packed into an incredibly dense structure. Some neutron stars rotate rapidly and emit beams of radiation, known as pulsars, which can still be detected even in this late stage of cosmic evolution. Black holes, however, become the most dominant objects in the universe over very long timescales. They grow by absorbing matter, merging with other black holes, and capturing remnants of stars and planets. In the absence of new star formation, black holes slowly consume the remaining structures within galaxies. As a result, galaxies gradually become dominated by black holes and stellar remnants. Over time, even stars that are no longer active can be disrupted by passing close to black holes. These events, known as tidal disruptions, can tear apart stars and feed material into black holes, producing brief bursts of energy. Despite this activity, the overall energy output of the universe continues to decline. The universe is becoming increasingly dark, not because light disappears instantly, but because the sources of light are gradually extinguished over time. Fewer new stars are born, and existing stars continue to age and fade. The cosmic background radiation, which once provided a uniform glow across the universe, continues to cool and shift toward longer wavelengths. Over time, it becomes increasingly difficult to detect. Eventually, it will become so faint that it blends into the background of other low-energy processes. Meanwhile, dark energy continues to drive the expansion of the universe. This expansion is not slowing down. In fact, it is accelerating. Distant galaxies move away from each other faster and faster, eventually crossing beyond each other's observable horizons. This means that in the far future, observers within any given galaxy will only be able to see their own local, gravitationally bound system. This leads to a profound transformation in the structure of observable reality. The universe becomes divided into isolated islands of matter, each surrounded by an ever-expanding void. Communication between these islands becomes impossible over time, as the expansion of space prevents light or signals from traveling between them. Inside these isolated regions, time continues to pass and physical processes continue to unfold. However, the overall complexity of the universe decreases. Star formation has ceased. Galaxies are no longer merging with distant systems, and the large-scale structure of the universe becomes effectively frozen in its local configurations. As this continues, black holes become increasingly important. They are among the last remaining dynamic objects in the universe. Over extremely long timescales, even they begin to evolve through quantum processes. According to current theoretical understanding, black holes are not completely stable. They slowly emit radiation through a process known as Hawking radiation. This radiation causes black holes to lose mass over time. As they shrink, they become hotter and emit more radiation, accelerating their evaporation. In the final stages of this process, black holes may release a burst of energy before disappearing completely. This represents one of the last major energetic events in the universe. After black holes evaporate, what remains is a universe filled with extremely low energy particles and radiation. There are no stars, no galaxies, and no large-scale structures in the traditional sense. Matter becomes increasingly diffuse, and interactions between particles become extremely rare. This state is often described as the transition toward the universe's final equilibrium. It is a state where energy differences are minimized and no significant sources of free energy remain to drive large-scale processes. The universe becomes dominated by entropy, with no organized structures capable of sustaining complex activity. Yet, even in this distant future, the universe is not completely static. Quantum processes still occur, particles still interact occasionally. Fluctuations in space-time may still happen on extremely small scales. But these events are rare and do not lead to the formation of new large structures. This chapter represents a critical transition in cosmic history. It is the era where the universe moves from one dominated by active stellar processes to one dominated by remnants and long-term decay. It is a universe that still exists and evolves, but in a slow and increasingly quiet manner. In the next stage of this journey, we will explore the far future of the universe, where even the last remnants fade away, black holes evaporate, and the cosmos approaches its ultimate fate in a state of extreme emptiness and minimal energy. As the universe moves further into its distant future, it enters one of the most profound and quiet phases in its entire history. All the grand structures that once defined cosmic evolution, galaxies, active star systems, nebulae, and vast clouds of interstellar gas, have now largely disappeared or transformed into remnants of their former selves. What remains is a universe dominated by the after-effects of earlier eras, where energy is scarce, activity is minimal, and change occurs on timescales so vast that they are difficult to imagine. At this stage, the universe is often described as entering the era of black holes and degenerating matter. This is because the majority of luminous energy-producing objects have already completed their life cycles. Stars have exhausted their nuclear fuel, galaxies have stopped forming new stars, and the interstellar medium has been stripped away or consumed. The remaining structures are primarily stellar remnants, with black holes becoming the most significant gravitational features in the cosmos. White dwarfs, which were once the final state of stars like the Sun, continue to cool and fade. They no longer produce energy through fusion and instead rely on residual thermal energy slowly radiating into space. Over time, they become colder and dimmer, eventually becoming virtually invisible as they approach the temperature of the surrounding cosmic background. Neutron stars also persist in this era. These incredibly dense objects, formed from the collapsed cores of massive stars, continue to exist as stable remnants of earlier supernova explosions. Some neutron stars may still rotate rapidly, emitting beams of radiation as pulsars, but even these signals gradually weaken as rotational energy is lost over time. Despite the persistence of these remnants, black holes begin to dominate the cosmic landscape. They are the most stable and long-lived objects known in the universe under current physical theories. Unlike stars or planets, They do not rely on internal processes such as fusion or chemical reactions. Instead, they are defined by the geometry of space-time itself. Black holes grow over time by absorbing matter and merging with other black holes. In the absence of new star formation, they begin to consume the remaining stellar remnants and stray matter within galaxies. Over extremely long timescales, galaxies themselves can effectively be reduced to collections of black holes and faint cooling objects. As black holes merge, they produce powerful bursts of gravitational waves. These waves are ripples in the fabric of space-time, generated by the acceleration of massive objects. The detection of gravitational waves in earlier cosmic eras provided direct evidence of black hole mergers, but in this distant future, such events become increasingly rare. Eventually, most black holes in a given region will merge into a few extremely massive objects. In some cases, entire galaxy clusters may collapse into a single supermassive black hole. These objects represent the final stage of gravitational collapse on large scales, containing enormous amounts of mass compressed into extremely small regions of space. At this point, the universe is no longer structured in the way it once was. The cosmic web that defined the large-scale distribution of galaxies has dissolved into isolated regions dominated by dark, compact objects. The vast spaces between these regions continue to expand due to dark energy, pushing them farther apart and reducing any possibility of interaction. The accelerating expansion of the universe plays a critical role in this stage. As space itself expands faster over time, distant regions move beyond each other's observable horizons. This means that light, or any other signal emitted from one region, can no longer reach another. Each gravitationally bound system becomes isolated from the rest of the universe. Within these isolated systems, evolution continues, but in a limited and increasingly constrained way. Black holes remain the primary active objects. They can still interact with nearby matter, absorb remnants of stars, and merge with one another. However, the overall amount of available material decreases over time. One of the most important processes in this era is the gradual evaporation of black holes through quantum effects. According to theoretical physics, black holes are not completely stable. They emit a faint form of radiation due to quantum processes near the event horizon. This phenomenon, known as Hawking radiation, causes black holes to slowly lose mass over time. As a black hole emits this radiation, it gradually shrinks. The smaller it becomes, the faster it loses mass, leading to an acceleration of the evaporation process. For large black holes, this process takes an extraordinarily long time, far exceeding the current age of the universe. But given enough time, even the largest black holes will eventually evaporate completely. In the final stages of evaporation, a black hole becomes extremely small and hot. It emits intense radiation in a short burst before disappearing entirely. This event represents one of the last significant energy releases in the universe. Once all black holes have evaporated, the universe enters an even more extreme state of emptiness. There are no longer any stars, no galaxies, and no black holes. What remains is a vast, expanding space filled with low-energy particles, radiation, and extremely sparse matter. In this state, the universe is often described as entering the dark era or the era of low-energy physics. The temperature of the universe continues to drop as expansion stretches the wavelength of radiation to extremely long scales. Eventually, even the cosmic background radiation becomes so diluted that it is effectively undetectable. Matter itself becomes increasingly rare. Protons, electrons, and other stable particles may persist for extremely long periods of time, but some theoretical models suggest that even these particles may eventually decay. If proton decay occurs, then all ordinary matter will eventually disintegrate into lighter particles over vast timescales. If matter decays completely, the universe would consist only of radiation and fundamental particles moving through an expanding, increasingly empty space. In this scenario, structure as we understand it would no longer exist. There would be no atoms, no molecules, no stars, and no possibility of forming new complex systems. Even in such a state, the universe would not be completely devoid of activity. Quantum fluctuations would still occur. Particles would still interact occasionally. Virtual particle pairs could still appear and disappear in the vacuum. However, these processes would be random, isolated, and not capable of producing large-scale structure. As time continues, the universe approaches a state of maximum entropy. Entropy is a measure of disorder, or the number of possible microscopic configurations of a system. In the far future, entropy reaches extremely high levels, meaning that the universe becomes highly disordered and energy differences are minimized. This state is often referred to as heat death, although it is not a sudden event but a gradual process. In heat death, there are no significant energy gradients to drive physical processes. Without energy differences, there is no mechanism for sustained activity, structure formation, or complexity. However, even this concept has nuances. The universe is still governed by quantum mechanics, and on the smallest scales, fluctuations may still occur. Some theories suggest that rare quantum events could lead to temporary decreases in entropy, although these would be extremely unlikely and short-lived. In addition, some speculative models of cosmology suggest that the universe may not end in a simple state of complete uniformity. Instead, quantum fluctuations over extremely long timescales could potentially lead to new regions of low entropy, possibly giving rise to new expanding systems. These ideas are highly theoretical and not part of the standard cosmological model, but they highlight the ongoing uncertainty about the ultimate fate of the universe. What remains clear in this stage is that the universe has undergone a profound transformation. From a hot, dense, rapidly expanding state filled with energy and particle interactions, it has evolved into a vast, cold and dark environment dominated by remnants and decay. The processes that once created stars and galaxies have long since ceased, and the universe has entered a phase where change occurs only slowly and rarely. This chapter represents the near-final stage of cosmic evolution. It is a universe where structure still exists in limited forms, but where the forces that once drove complexity have largely run their course. Black holes dominate, matter fades, and space continues to expand, carrying the universe toward an increasingly empty future. In the final chapter of this journey, we will explore the ultimate fate of the universe itself, where even the last traces of matter and energy may disappear, and where questions about existence, time, and reality reach their deepest and most fundamental limits. In the farthest reaches of time that physics can meaningfully describe, the universe enters a stage where nearly all familiar structures have already vanished. The bright, active cosmos of galaxies, stars, and black holes has faded into an almost unimaginable emptiness. What remains is a universe that is still expanding, still evolving in a mathematical sense, but almost completely devoid of the energy and structure that once defined its earlier eras. This is the transition into the deep future, where the last traces of matter and radiation are stretched thin across an ever-growing void. At this stage, space itself has become the dominant feature of reality. The expansion driven by dark energy continues without slowing, causing all unbound regions of the universe to move farther apart at an accelerating rate. Galaxies that are not gravitationally bound to each other have long since passed beyond each other's observable horizons. Even light emitted from distant regions can no longer bridge the expanding gaps between isolated cosmic islands. Each gravitationally bound system, such as a galaxy remnant or a cluster of stellar remnants, exists effectively alone. Within these isolated regions, the final stages of astrophysical evolution unfold. By now, most stars have exhausted their nuclear fuel. Red dwarfs, the longest-lived stars in the universe, have also begun to fade. These small stars, which once seemed nearly eternal compared to their massive counterparts, eventually run out of hydrogen and cease fusion entirely. When this happens, they transition into dim stellar remnants, no longer able to produce light or heat in any significant quantity. White dwarfs, which are the remnants of sun-like stars, continue their slow cooling process. Over extremely long timescales, they lose their remaining thermal energy and fade into darkness. Neutron stars, once among the most extreme objects in the universe, also gradually lose their energy through radiation and particle emission, though they remain stable for immense periods of time due to their dense structure. Black holes now represent the most significant remaining objects in the universe. Almost all other forms of structure have either been absorbed into them or have drifted away into isolation. Black holes continue to grow by consuming nearby matter, but as the universe expands and matter becomes increasingly scarce, their growth slows significantly. Eventually, even black holes become isolated, cut off from any meaningful external sources of material. At this point, black holes begin to dominate the structure of their local regions completely. Entire galaxies have already collapsed into supermassive black holes at their centers, surrounded by sparse halos of stellar remnants. Smaller black holes from previous stellar evolution continue to orbit or merge within these systems. Over time, gravitational interactions cause many of these black holes to merge, forming even larger and more massive objects. These mergers are among the last dramatic events in the universe. When two black holes collide, they release enormous amounts of energy in the form of gravitational waves. These waves propagate through space-time, carrying information about the motion and properties of the merging objects. However, as time progresses, and the universe expands further, such events become increasingly rare. Eventually, most black holes within a gravitationally bound system will merge into a single dominant black hole. This object may contain the combined mass of billions of stars and countless smaller remnants. It becomes the central feature of its region of space, surrounded by an increasingly empty environment. Outside these isolated systems, the universe continues to expand at an accelerating rate. Dark energy, which drives this expansion, causes space itself to stretch faster over time. This means that even light emitted from distant objects cannot overcome the increasing separation between regions. The observable universe for any given observer shrinks over time, not because space itself is contracting, but because expansion is pushing everything else away faster than signals can travel. This leads to a profound change in the nature of observation. In earlier eras, astronomers could observe galaxies across vast distances, reconstructing the history of the universe by studying distant light. In this far future, such observations become impossible. Only local gravitationally bound systems remain visible. The rest of the universe becomes effectively invisible, not because it disappears, but because it moves beyond the reach of any possible signal. Within these isolated regions, black holes slowly evolve through a process that becomes increasingly important on cosmic timescales. According to quantum theory, black holes are not completely stable. They emit a very faint form of radiation due to quantum effects near the event horizon. This process, known as Hawking radiation, causes black holes to gradually lose mass over extremely long periods of time. As a black hole emits this radiation, it slowly shrinks. The rate of evaporation increases as the black hole becomes smaller, leading to an accelerated loss of mass in its final stages. For supermassive black holes, this process can take timescales that are unimaginably long, far exceeding the current age of the universe by many orders of magnitude. However, given enough time, even the largest black holes will eventually evaporate completely. When a black hole reaches its final stages of evaporation, it becomes extremely small and hot. It emits a final burst of high-energy radiation before disappearing entirely. This event marks one of the last significant energetic processes in the universe. After this point, no black holes remain. With the disappearance of black holes, the universe enters an even more extreme phase of emptiness. All major sources of gravitational structure and energy have now vanished. What remains is a vast, expanding space filled with extremely low energy particles, radiation, and possibly stable remnants of matter. Depending on whether certain particles, such as protons, are stable or eventually decay. If protons are stable, then matter can persist in extremely diffuse forms for unimaginable timescales. Atoms may continue to exist in isolation, drifting through space with no possibility of forming new structures. However, if proton decay is possible, then even atoms will eventually disintegrate, breaking down into lighter particles such as positrons, photons, and neutrinos. In either case, the universe becomes increasingly featureless. The density of matter approaches extremely low levels, and interactions between particles become extraordinarily rare. The universe is not completely empty, but it is effectively devoid of organized structure. Radiation that once filled the universe, including the cosmic microwave background, continues to redshift due to expansion. Its wavelength becomes longer and longer, its energy decreasing over time. Eventually, it becomes so diluted that it is indistinguishable from the background of quantum fluctuations. At this stage, the concept of temperature itself becomes less meaningful on large scales. Without significant energy exchanges between systems, there are no thermodynamic gradients to define a meaningful direction of heat flow. The universe approaches a state of near thermodynamic equilibrium, where all accessible energy differences have been minimized. This is often referred to as the approach to heat death. However, it is important to understand that this is not a sudden event, but a gradual process that unfolds over an almost infinite timescale. The universe does not end abruptly. Instead, it slowly transitions into a state where no significant macroscopic processes can occur. Even in this extreme state, the universe is still governed by physical laws. Quantum mechanics still operates at the smallest scales. Particles still fluctuate in and out of existence due to vacuum energy. Space-time itself may still undergo tiny fluctuations, but none of these processes lead to the formation of long-lived structures or meaningful large-scale change. Some speculative ideas in theoretical physics suggest that even in this seemingly empty universe, rare quantum events could have dramatic consequences over extremely long timescales. For example, random fluctuations might, in principle, create temporary low-entropy regions or even isolated pockets of structure. However, such events would be extraordinarily rare and would not alter the overall trend toward equilibrium. As time continues, the universe becomes increasingly dominated by randomness and isolation. Any remaining structures are separated by vast distances, and interactions between them become effectively impossible. Each region evolves independently, governed only by local conditions and extremely rare quantum events. This chapter represents the deepest stage of cosmic evolution that can be meaningfully described using known physics. It is a universe that has lost nearly all of its active structure, where black holes have evaporated, stars have faded, and matter itself may be dissolving into its most basic components. Yet even in this profound emptiness, the universe still exists. Space continues to expand. Time continues to pass. Physical laws remain in effect. But the richness of structure, the complexity of interactions, and the dynamic processes that once defined cosmic history have all faded into near silence. In the final chapter, we will explore the ultimate fate of this universe, where even the smallest remnants of structure and energy may disappear, and where questions about existence itself reach their most extreme and speculative limits. At the deepest horizon of cosmic time, the universe reaches a state that stretches both imagination and theory to their limits. This is not an ending in the everyday sense, not a moment where something suddenly stops, but a final phase where all processes slow toward near complete stillness. It is the culmination of everything that began with the first expansion, the final transformation of a universe that once burned with energy, formed galaxies, created stars, and gave rise to complexity on every scale. In this final era, the universe is dominated by extreme emptiness. Space itself has expanded so much that all gravitationally bound structures are isolated from one another. Each surviving system, whether it is a remnant galaxy cluster, a lone black hole remnant, or a sparse collection of degenerate stars, exists in complete isolation. No light or signal can cross the vast gaps between these regions, because expansion has stretched space faster than any possible information can travel across it. Inside these isolated regions, the last traces of matter continue to exist for a time. If proton decay does not occur, then atoms may persist in extremely stable forms, but they remain widely separated and inactive. If proton decay is possible, then even these atoms slowly disintegrate, breaking down into lighter particles such as electrons, positrons, photons, and neutrinos. Over unimaginable timescales, even the concept of stable matter fades. White dwarfs, which once represented the final stage of stellar evolution, have long since cooled into cold, dark objects. They no longer emit visible light or significant heat. Their internal energy has radiated away into space, leaving behind inert remnants drifting in the darkness. Neutron stars, once among the densest objects in the universe, also gradually lose their energy through extremely slow processes, including particle emission and potential quantum decay channels. Black holes, which once dominated the universe during intermediate eras, have already undergone their final transformation. Through Hawking radiation, they slowly evaporated over vast timescales, shrinking until they disappeared entirely. Their final moments released brief bursts of high-energy radiation, but those events are now long past. With their disappearance, one of the last major sources of gravitational and energetic structure has been removed from the universe. What remains after black hole evaporation is a universe composed primarily of extremely low-energy particles and radiation. Photons that once carried the cosmic microwave background have been stretched by expansion to wavelengths so large that their energy is effectively negligible. These photons still exist, but they are so diffuse and so low in energy that they no longer play any meaningful role in physical processes. Neutrinos, which interact very weakly with matter, drift through space almost entirely unimpeded. Electrons and positrons may still exist in isolated regions, but they are so widely separated that interactions between them become extremely rare. The universe is no longer structured in any conventional sense. It is a sparse sea of nearly non-interacting particles embedded in an ever-expanding space-time. At this stage, the concept of structure itself begins to lose meaning. Galaxies, stars, planets, and even atoms were once organized systems with internal complexity and interactions. Now, any remaining particles are effectively isolated points with no larger organization. The universe has transitioned from complexity to simplicity, from interaction to isolation, from energy-rich processes to near-complete stasis. The expansion of the universe continues due to dark energy. Space itself stretches outward, increasing the distance between all unbound regions. Unlike earlier eras, where gravity dominated local structure formation, dark energy now defines the large-scale behavior of the cosmos. Its effect is subtle on small scales, but overwhelming across cosmic distances. As expansion continues, the observable universe for any given observer shrinks not in physical size, but in accessible content. Distant regions move beyond the cosmological horizon, meaning their light and information can never reach other regions again. Over time, each gravitationally bound system becomes a completely isolated island of space-time, surrounded by an ever-increasing void. In the far future, even the concept of observation becomes fundamentally local. No observer can detect galaxies outside their own local gravitational system. Eventually, even that system fades into darkness as all luminous sources disappear. The sky becomes empty not because space ceases to exist, but because all sources of detectable radiation have vanished or become unreachable. Despite this extreme emptiness, quantum physics ensures that the universe is never completely static. Vacuum fluctuations still occur at the smallest scales. Particle and antiparticle pairs can briefly appear and annihilate. Space-time itself may exhibit tiny fluctuations due to quantum uncertainty. However, these events are random, short-lived, and do not lead to the formation of long-lasting structures. Some speculative theories in cosmology suggest that even in this seemingly final state, the universe may still allow for extremely rare events over unimaginably long timescales. Quantum fluctuations, given enough time, could theoretically produce temporary decreases in entropy or even brief reconfigurations of local space-time. However, such events would be so rare that they would not alter the overall trend toward equilibrium. This leads to the concept of the universe approaching a state of maximum entropy. Entropy is a measure of disorder, or the number of possible microscopic configurations that correspond to a macroscopic state. In the far future, the universe reaches a point where entropy is maximized, meaning that all accessible energy differences have been smoothed out. In this state, there are no significant gradients of temperature, pressure, or energy to drive physical processes. Without energy differences, there is no mechanism for sustained motion, structure formation, or evolution on large scales. The universe becomes thermodynamically uniform, with no preferred direction for change. This is often referred to as heat death, but it is more accurately described as a state of thermodynamic equilibrium on cosmic scales. It is not a moment of destruction, but a gradual fading into uniformity. The universe does not stop existing. Instead, it reaches a condition where meaningful change becomes statistically negligible. Even in this state, the universe still exists in a mathematical sense. Space and time continue. Quantum fields still fluctuate. But the rich tapestry of cosmic evolution has been replaced by near-perfect simplicity. All major sources of structure and energy have already been exhausted. Some theoretical frameworks in physics explore the possibility that this state may not be absolutely final. Over extremely long timescales, quantum fluctuations could, in principle, give rise to rare low-entropy events. In some speculative models, these fluctuations might even create isolated regions where new cosmic expansion could begin. These ideas are highly theoretical and not supported by direct evidence, but they illustrate the depth of uncertainty that remains at the boundaries of cosmology. Another idea sometimes discussed is the possibility that the universe could undergo a phase transition in the far future. If the vacuum state of the universe is not perfectly stable, it could transition into a lower energy state, fundamentally changing the laws of physics. Such an event, known as vacuum decay, would propagate at the speed of light and reshape space-time itself. However, there is currently no evidence that such a transition is imminent or even likely within any meaningful timescale. In the most conservative and widely accepted view, the universe continues to expand forever, gradually approaching a state of maximum entropy where all structures have decayed, all energy has been diluted, and all processes have slowed to near complete inactivity. This is the ultimate fate of a universe governed by known physical laws. What remains at the end is not a dramatic conclusion, but a quiet and almost featureless expanse of space-time. No stars shine, no galaxies form, no black holes remain. Only extremely low energy particles and radiation drift through an ever-expanding void. The universe becomes a place without events, without change, and without structure. Yet even in this final state, the universe still contains the full history of everything that came before it. The expansion from the Big Bang, the formation of particles, the birth of stars, the growth of galaxies, the emergence of black holes, and the eventual decay of all structures are all embedded in the evolution that led to this point. The present state of the universe is the consequence of its entire past. In this sense, the universe is not defined only by its final condition, but by the complete sequence of transformations that shaped it. The final era is simply the last step in an ongoing process that began with a state of extreme density and energy, and progressed through layers of increasing complexity before returning to near simplicity. This final chapter represents the end of observable cosmic evolution under known physical laws. It is a universe that has expanded, cooled, organized itself into structures, and then slowly dissolved those structures over unimaginable timescales. It is a universe that has moved from creation to complexity and finally to near complete emptiness. And yet, even in this extreme future, one question remains open. Is this truly the final state of existence, or is it only one phase in an even larger and deeper cosmic cycle that lies beyond our current understanding?